Hi, and welcome to this session on motion patterns with parametric equations. My name is Mariano Gomez. I'm a Microsoft Business Applications MVP. And as part of this introductory session, what I want to really do is show a couple of the things that I've been working on in PowerApps, primarily around the use of parametric equations to capture motion and to describe motion patterns that are otherwise complex. So the first thing I want to do is I want to show you what I've been up to. And this is my PowerApps application. Today I'll be covering three different types of motion patterns, so four different types. First is the Lissajous curve. Second one is the rose curve. And I'll talk about the spiral curve and the Hypothrochoid curve. Now, this is a standard menu window. As you can see, all I have is four buttons here, but I'll start by clicking on the Lissajous curve. In the Lissajous curve, I allow the users to set parameters to different types of variables that will define the motion pattern, and those are basically interrelated, so any change to these variables define how this particular circle is going to move, or this particular point is going to move on the screen. So if I click start here, initially you can see that my A and B values are actually the same for this particular motion pattern, which caused the circle to move in a linear way from one side of the screen to the other. Now if I start to vary those different parameters, this will basically generate different types of motion. The ranges are very sensitive between A and B, so depending on some of these values, you get different motion patterns. The most important thing here, though, is if I start to change, let's say, the value of B, then that will basically amplify the motion of the figure itself, of the object itself. And I can also change the value of D in terms of values of pi, which will then define the type of equation that I'm parametric equation that I'm creating. So the most important thing to note here is how these particular changes affect the motion pattern that I am defining. So for example, here I change the value of A, and that creates a different movement. So I can also simplify the value of B from 3 to 1, which would then, alter, first and foremost, it alters the harmonics of the curve, which makes it a much smoother move. But I can also alter the amplitude on the x-axis, which will then also change that motion. So there are some very interesting applications of these type of equations, and we'll talk about that as our second part of this. So I'm just going to stop this, and I will go back to my original screen. And now let's take a look at the rose curve. The rose curve mostly defines a number of petals, and those petals sort of create different motion patterns as well. So for example, here I have a petal value of 2. So this is only a rose of 2 petals, and it moves accordingly. But I can vary the number of petals, which will then also vary the speed of the creation of that curve, but it will also show the different touch points on the circle that I use as a reference for you to see the number of petals that are being created. We can change this to something a little bit more or less fast by altering the number of petals to 4, for example, which will then show you how that curve behaves. So all in all, pretty interesting stuff. I can stop this here and go back to my main navigation, and then you'll see now the spiral curve. So I have some preset values. I can define the tightness, and I can define the orientation that I want for that particular curve. If I start here, since my tightness is just 1, it will appear to be very tight, but you can see it unraveling slowly based on that tightness value. I can increase the tightness value here, so we'll make it less tight, more loose, and then you can see that that particular object now it starts to increase, and you can see the value of x and y changing based on that motion pattern. So we can also change the orientation. So if we want to do 2, that will basically expand a little bit the orientation. If I can do -1 as well, you know, those values will change accordingly. So all in all, interesting motion. If we go back to the main screen again, we can look at the Hypertrochoid. That's a very interesting figure. So if we start to look at how this works, we can vary the different ranges between A and B and H. So here we're going to say this is 30, this is 20. So we'll take a look at the motion pattern more articulately. So that's those are some consistencies that you can see. Let's just open this up a little bit. I have to take a look at, yep, there you go. So that's a good value that we can use for H. And that describes various motion patterns that are, depending on the ratio between A and B, change differently. So if I switch this to 300, then you'll see that that motion pattern starts to alter as well. So let's go here, 15, 14, change that value, and let's change this to 200 instead, and let's change this down to 5. So you can observe different motion patterns based on what those values of A and B are. Let's go down to 1 and 2. So as you can see, those values change, so I can significantly alter how this behaves or how it comports based on the number of values that we have here. So 10, yeah, there we go. So you can start to see that pattern behaving more interestingly, as if it were jumping in within a roulette, which is really what this curve is. Awesome. So we can stop this and go back. So let's talk about how we built this application. I think for the most part, I don't need to explain most of it, but let's talk about the Hypertrochoid. There are some fundamentals that I want you to keep in mind here before we get started with this. Or the Lissajous curve, I should say. It's also known as the Lissajous figure, and as you can imagine, it's a complex harmonic motion in itself, and it was investigated by Jules Antoine Lissajous back in 1857. The bottom line is the parameters for X and Y, which will then determine the motion on the screen, are basically affected by the values of A times the sine of A and by T plus D pattern delta, and we'll see how those are handled within our application itself, but keep that in mind. Also B, which will determine how the the amplitude of how this particular motion is going to behave on the y-axis, times the sine of B by T. B and T being different values that provide some sort of determine the motion pattern in itself. Okay, and here are different values of A and B that will cause different motion patterns. So that ratio is 1 to 2 between A and B. So if I set these motion ratio values, I should be able to get these different movements based on these parameters. So here are more complex values. The more A and B become interrelated, the higher those values become, then you get different motion patterns that affect the Lissajous curve. So how did we implement this? So here for the hypertrochoid, I'm sorry, for the Lissajous curve, I have actually set up the screen, and we have a number of parameters here. I have added actually a slider to control the value of A based on the equation parameter that you saw before, and the value of B. And I have allowed users to enter the value for A and B, which are basically control the amplitude of that curve. So here we go back. We can see that I have added also a text input box that allows users to enter the value of pi, or basically multiples of pi. We have a start button, a stop button. We've added a timer, and I'll explain the importance of the timers here. And we have added a back button that basically all it does is it really sends us back to the navigation. We'll run the macros in the stop button and navigate back to the main screen. So that's important to keep in mind. So we use a slider control for the values of A and B, and we allow you to enter values for A and B, which control the amplitude, how far up or down this circle is going to move in respect to the X and Y axis. And finally D, which is a delta that basically allows you to control how the overall motion inside the curve is going to behave. All right, so what do we do with that? So the main aspect here is we want to control the t parameter in the equation. So if we go back here, that t parameter is going to be mainly what drives the overall motion movement. I have added also a collection, and that collection in essence is going to capture simply the plot points for X and Y. So I had in mind at some point to just retrace the path that the figure or this object takes around the screen. So I figured I would use a collection to capture all the X and Y values that are being produced as a result of the equation. All right, and then the other thing that we have here is a disable stop. That's for the timer itself, and we go from there. Okay, so let's see what happens when we click the start button. When we click the start button, what I do is I clear my collection and I update the context for that timer. I want to make sure that the timer start, that value, the variable my timer start is set to true, which will then basically force that timer to start. Okay. If we go back here, we also want to change the display mode to edit. So that's for the stop button. So the stop button does not basically become enabled until I hit start. So you can then, it gives the user less things to worry about while the application is in works or still. So now that we know this, let's take a look at the equation itself. So how do we get the values of X and Y for this particular circle or for this particular object on screen? So if I go and I look at the X property, we'll see that the X property pretty much is a rehash of the equation. So what I've done is I've taken the form factor width divided by 2. Form factor width divided by 2 is simply a calculation that I do about the resolution of the screen, and I basically add 100 times the A parameter. So that's basically is going to amplify the value of A, times the sine of the A parameter slider value, times theta, which is the angle determined by the motion of the timer itself, and we'll talk about the timer itself in a bit. And we add the D parameter, which is simply a multiplier of pi. So that's pretty good. We round that out to make sure that we have discrete values for the X position, and simply for the Y position we program a very similar form factor divided times or the height of the form factor divided by 2 plus 100 times the value of the B parameter. So we amplify whatever is in these values by 100 initially. You could choose to set whatever motion value you want, and then times the sine of the parameter slider times the angle, which is determined by the motion in the timer, and times the theta, which is the value of the T parameter. So since we've talked about the timer itself, let's take a look at what goes on here. The most important thing here is when the timer starts, what we want to do is we want to update the theta variable by steps or increments of 0.05. So every time the timer ends, that timer basically is going to collect or update the coordinates within the collection, so we don't have to worry about losing the position of where the object was on the screen. All right, now the most important thing here is I've set a duration of 1, and I've had actually this timer repeat every single time the duration is over. So the good thing is here is every time we reach 1 millisecond in duration, the timer is going to repeat. But on the timer start, every time the timer starts, we actually updating the value of theta. So basically that's going to start creating the motion based on the angle. If you kind of remember what the equation looks like, it's going to actually take that angle and keep incrementing the value. So each time I will have a different value of for this sine position, or for the sine value of the angle itself, times the multiplier, which will then update my x coordinate on the screen. Likewise, this will update my b coordinate on the screen based on the value of t. So as you can see, it's pretty straightforward what we've done here. The most important thing is to play with this timer control to ensure that we are incrementing the value of that angle every single time the timer is reset. So now the stop itself, the stop button itself, will then basically stop the timer and change the value of theta back to 0, so we can play with this as many times as we want. Back will simply navigate back to the menu, but just for the sake of making sure that this is done correctly, we also running whatever formula or macro we wrote for the start button, in this case updating the context of the start timer start, and certainly updating the value of zeta, resetting the value of zeta. So that's good. So these are pretty simple equations in general to program. The row screen is very similar as well. Here the only thing we keep track of is the number of petals that we want to increment. But likewise, on the position of the circle, if we look at x, what we're doing here simply is we actually using the form factor width. We're amplifying this by 300 times the cosine of the number of petals per arm that we dictate, theta, which is actually also a function of the timer, and we'll see how we control the step as well, or the increments for that variable, which are pretty similar to what we did for the Lissajous curve, and we take the cosine of that. So that's pretty cool. 300 simply dictates that we're going to move the circle around a circle of a radius or diameter of 300, but you can increase and play with those values however you want in your parameter. You could actually make this a dynamic parameter as well, so users have the ability to input what they, how wide they want the circle to move across the screen. All right, so let's look at the start value. Same thing here. I've grouped these controls, but the start value will basically clear the plot points collection, it will update the context to the timer start itself, and then it will actually set the disable mode to edit for the stop button, so I can press it once I've initiated the motion. Alright, stop will then in essence basically stop the timer and reset the value of theta itself, which is the d value for the angle. Back will take me back to the previous screen, not before running the macro in the stop button. So once again we come down to the timer itself. So as you can see, I haven't done anything different in this particular on timer start. All I'm doing is I'm actually increasing the angle steps by 0.05 radians, and on timer end, all I'm simply doing is collecting the coordinates for the plot points or where the position of the circle on the screen at that point. Alright, same thing here. I've actually set the duration to 1, and I have this to actually repeat. So every time I reach a duration of 1 millisecond, automatically this will repeat. Therefore, every time the timer starts, I'm incrementing the steps, and at the end I'm collecting the plot points of where this circle is. So that's pretty interesting. For the spiral curve, again pretty similar in nature. The only thing here is the tightness. The tightness basically determines the aperture or closeness between the loops while the spiral is unraveling, and the orientation determines whether it's gonna basically unravel from clockwise versus counterclockwise. That's kind of how that operates. Now here we also have a start button that's gonna basically update the context for the timer start. I'm gonna set that to true, and we're then going to update the context for the stop button. We're gonna enable that. Stop will then basically reset both the timer and stop the timer and reset the angle value for theta. And finally here, and the only thing here that is slightly different is we actually, on the timer start, we incrementing the angle steps by 0.1 radians instead of the previous 0.05 radians to make it more harmonic in its motion. At the same time, this also has a duration of 1 millisecond, and it has an auto repeat value, or the repeat value set to true, so each time we update the context of the position determined by the angle in radians. Okay, so I feel that here on the circle itself, if you look at the parameters for this, we also actually taking the tightness parameter, multiplying that by the angle itself times the cosine of the angle plus the orientation parameter, and in essence that will determine what that motion is going to be. Likewise, we have also done similar for the y parameter. So this one, instead of using the cosine, we're actually doing the sine plus the orientation of the angle plus the orientation parameter as well. So now on our hypertrochoid, this one is very elaborate, but pretty much we have a relationship of the of A, B, and H. And I am going to slide over to my slides. So if we look at the Rose curve, we talked about this one. This is kind of the value of the equation, cosine of kt times cosine t, and for y it's going to be cosine of kt sine of yt. So we talked about that. Now let's look at the hypertrochoid, which is a little bit more of an involved equation, where you have basically the value of a minus b times the cosine of t plus h times the cosine of t by a minus b over b. So that basically determines the different steps and motions of based on those relationships of a, b, h, and certainly t as an angle. Okay. So this is basically concluded my demonstration of how you would set up these parameters. Uh, this particular project is available for download from the PowerApps community website. So if you go to the PowerApps community website, you are able to get a hold of these, download them, play with them in your environment, and certainly determine how you can best use some of these things in your daily work, especially if you are working with games or you have special projects that involve math. This is a good way to show how PowerApps can take advantage of math to create motion overall for your different projects. So thank you very much for watching, and I'll talk to you soon.